So in ensemble learning, we talked about bagging and stacking in the previous classes. So today we will cover about boosting. We will know what boosting actually means is the idea behind boosting, and we will also talk about different boosting methods that are available. So we are going to learn about ADA boosting, and also we will learn about uh, gradient boost techniques. So there is another boosting technique which is XG boost, and that needs some knowledge on linear regression and logistic regression topics as well, as we haven't covered them. We are going to see the technique of boosting after completing the linear regression and logistic regression. So with that, for today's session, we want to understand what is the idea behind boosting. So boosting is a sequential training model. That means how does this actually works is, if you look at this particular diagram, you see this is the training data that we have picked. So we want to um, do the classification on this training data. So we pass we pass this data through a weak learner which predicts some output. So it comes up with some prediction, right? So it might have done some wrong classifications. So those which are those records which are wrongly classified will be given higher weightage in the next iteration. Okay, so whichever records or whichever items are wrongly classified, they will be given high weightage in the second iteration. Again, the data will be passed through a linear prediction model. And again, once that output is predicted, in that particular output, whichever records are wrongly classified, again they will be given higher weightage for those records. And this sequence will keep on going at the end when once we construct multiple trees, right? Ensemble learning is all about combining multiple prediction models to get a better prediction. That is what ensemble modeling is. Whereas in boosting, we do that in sequential order, and in every iteration, the wrongly predicted records will be given higher weightage. Maybe this would be little clumsy for you right now, but once you see an example, you will understand how the weightage will be improved for the wrongly classified items. So the only thing that you need to understand is there are look at them as different training methods. Okay, so if you look at this is one classification model, and this is one classification model, and this is one classification model. So for every model, we are injecting the data to it. But how are we constructing this particular data for the second iteration? Here we are giving higher weightage to the records which are wrongly classified in the first iteration. So in the first iteration, whichever records are wrongly classified, they were given higher weightage, um, and that is used as an input for training the second model. Again, when we consider the second iteration output, in the second iteration output, whichever records are wrongly classified in the in the test data, in the training data, they will be fed as they will be fed. They will be given higher weightage for the third model's training data. So that is how boosting actually works. So if you look at this is the initial data set. It is fed to the first predictive model, and from the output given by the first predictive model, the second model's training data set will depend upon. So it will get more weightage, or when we say more weightage, the wrongly classified records will be created more times, or in some sort of sorry, some sort of weightage will be given for those records which are wrongly classified. You will shortly see that. So that is what boosting technique actually means is, so each new model corrects the errors in the previous model. That is the main idea behind boosting. So this is the new model, and what is its main agenda is, to correct the errors in the previous model. Okay, that is how sequence is established in boosting. So typically we will construct 100 such models. somewhere around 100 such models. So here you see three different models, one, two, three, and this model is trained by giving the is this model main intention is to eliminate or correct the errors made by the first model. So similarly, in the real world, we will construct hundred number of such trees or such models in the boosting technique. So it gives more weightage to the misclassified instances during training to improve performance. So more weightage to the misclassified instances. So how does it actually gives more weightage to the misclassified instances is what we are going to see now. Okay. So going back here. So the first technique that we're going to learn in the boosting is ADA boost technique. The full form of ADA boost is adaptive boosting. Okay, so let's compare with the random forest. Random forest is bagging technique, right? So we construct n number of trees and there is no restriction on any sort of leaves or something, right? So once we construct n number of decision trees, we will combine the output of each tree and we will classify that based on the voting. That's what we do in random forest. So if you compare the random forest with ADA boosting technique, so this is a simple comparison. In random forest, what you do each time you make a tree from the data, you make a full-sized tree, right? So you always create full-sized trees in the random forest. So there is no predefined depth in the random forest. So there is no constraint on the depth. You will construct full length trees or full size trees in random forest. Whereas in ADA boost technique, you will not construct full length trees or full size trees. The trees that you construct in ADA boost are just a node and two leaves. Okay, we call these as stumps. So this is how trees in Adabos technique is in Adabos technique will be constructed. You will not construct full-sized trees in Adaboosting. You will just construct stumps. A stump basically means is it will have one node and two leaves. That's all. So in Adaboost, you will only see stumps. You will never see full-size trees or any trees. There is a constraint for the Adobe Boost. In Adobe Boost, you can only work with stumps. Okay, so this is called as stump. Um, okay, so this is basically a tree, but this tree has just one node and two leaves. Such kind of tree is called as stump. If you go back here, um, if you take this particular example, here you have four columns. The first column is chest pain, Google blood. What is that? The second row is good blood circulation, blocked arteries, and the weight are the dimensions that are given. And heart disease is the label that is given for with the data. So based on these dimensions, we are deciding whether a person has heart disease or not. Okay, now we are trying to use AdaBoost technique to classify this particular data. How AdaBoost actually works is what we are going to learn now. But if as we are comparing the random forest with the AdaBoost trees, if you look at the tree constructed by the random forest, it constructs a full-size decision trees, right? So it constructs a full-size decision trees. Would take advantage of all the four variables that we measure to make a decision. So that means in random forest, we will use all the dimensions to construct the tree. And there is no restriction on how do we construct or the size of the the size of the tree. There is no constraint. This is how a tree or a decision tree in random forest will look like. But in AdaBoost, um, we use stumps and the stump can only use one variable to make a decision. So it cannot use all the four variables because in AdaBoost we only work with stumps, and the stump means it can make use of only one dimension or one variable. So this is how you will make stumps in AdaBoost. You will use only one dimension to come up with a tree or a stump. So stumps are technically weak learners, but AdaBoost actually likes that. That is how AdaBoost is designed, or how this technique actually works. Okay, so but how AdaBoost will achieve such a great accuracy in classification is that every stump is a weak learner, but we are combining multiple weak learners. That is what ensembling learning is. What ensemble learning will actually means is that it will actually combine multiple weak learners to do a strong prediction. Okay, so the ADA boost also will do the same, but it actually works on stumps. So it takes only one dimension into consideration, and it just takes only one dimension into consideration, and it works with only one dimension, that particular dimension. And to your knowledge, we we use the same techniques that we used in decision trees. Okay, how do ADA boost will comes up with only one dimension? It uses the same techniques that we have and that we have used for decision trees. If you remember, we used information gain. We calculated entropy for the parent and the leaf nodes, and then we calculated the information gain by subtracting the entropies, right? That is how we calculated the information gain for uh, each possible combination of the data in that particular dimension. And then we figured out and then we started by using a particular node which has highest information gain. So this all we discussed in decision trees. The same techniques will be used by the AdaBoost as well. Okay, so before going there, just look at this. In the random forest, each tree has an equal vote on the final classification. So once we construct n number of trees in random forests, full-sized decision trees will be constructed in the random forest. And once we constructed all the trees, how do we decide the final voting? So in the final voting, each tree will have the equal share, right? So let's suppose if I have 5 trees and 3 trees are saying that as a dog and 2 trees are saying that as a cat, we classify that particular image as dog in random forest. That means each tree has equal vote in the final classification. Okay. Whereas in the ADA boost, that is not the same. In ADA boost, some stumps will get more say. That means more weightage will be given for some stumps output, whereas some stumps output will be little low. So we combine all that and we come up with a particular number, and that say decides how do we classify in ADA boost. If you look at this, just to illustrate, I have created this image as a little larger one when compared to this particular stump. What that actually means is that this actually illustrates these stumps will have more say when compared to this particular stump. Okay, so this stump will get to be short, this stump will get more say when compared to this particular stump. That means the weightage for the output of this stump will be more in classifying the or in getting the final output when compared to this particular stump. Let's suppose if to predict the output of a particular data that we constructed 6 stumps. In the 6 stumps, all the 6 stumps will not get the same weightage. This stump, let's suppose this stump might have got the weightage of 0.4. This got 0.1. This got 0.05. Okay. This got somewhere around 0.3. This got somewhere around um, 0. You know, 2, 9, somewhere around. Let's suppose this is 0.05 again. This is somewhere around 0.02. That means the weightage for this particular stump is more when compared to all other stumps. That is what it all comes down to. So that is how the that is how AdaBoost stumps will have different amount of weightage when coming to the final classification. Whereas in random forest, it would be the same for all the trees. Okay. Um, in random forests, each decision tree is made independently of the others. We fed the data by shuffling the or by like replacement. I mean, what is that term? We do replacement, and then we construct the data in the random for the random forest, right, for the decision trees. So each decision tree is made independently. It will not depend on the output of the first decision tree. When we are constructing six decision trees in random forest, we will the second decision trees data will not depend on the first decision trees output. So they're all independent, whereas in ADA boost it is the different case. In contrast to like in contrast, in the forest of stumps made with data boost, order is important. The error that the first stump makes influence how the second stump is made. That's what we are talking about, the boosting, right? In boosting, the data that we fed to the second model depends on the classification made by the first model. So the predictions, the wrongly predicted data by the first model um, will have more weightage in the to the data that we fed to the second model. So that is how every stump or every tree in the data boost are interlinked, whereas in random forest they're all independent of each other. Okay, so in short, AdaBoost, what it will do is AdaBoost combines a lot of weak learners to make classification. Okay, so it combines a lot of weak learners to make the classification, and each weak learners are all are called as stumps. Okay, so each weak learner is is always a stump. So in the final classification, in the final classification, some stumps get more say in the classification than the others. That is what we have discussed, right? In the random forest, each one will have an equal say, yeah, or each tree will have the equal importance. Whereas in ADA boost, some trees will have, or some stumps will have more say when compared to the other trees. Okay, each stump is made by taking the previous stump's mistakes into account. How are we making the second stump? The second stump is being made by taking the output from the by considering the output of the first stump. So output of the first stump, which are wrongly classified, will be given more weightage. That is something which we have already discussed. Now switching into an example of on how this actually works. Okay, so this is the starting step for understanding the ADA boost. So to start understanding the ADA boost, we have taken an example data set. Okay, this particular data set has three dimensions. The first dimension is chest pain, the second dimension is blocked arteries, and the third dimension is patient weight. These three dimensions are used to predict the heart disease of a particular patient. Okay, now, so the first thing we do is give each sample a weight that indicates how important it is to be classified. It is to be correctly classified. Okay. So initially, each row will have the same weight. When we are constructing the first stump, each record will have the same weight. Okay. The reason being is only when we go to the secondary, then only we will know which has to be given higher weightages. That means whichever are wrongly classified will be given higher weightages. But in the first stage, every record will have the same weightage. We have the same responsibility of rightly classifying every output, because this is the first term that we are going to create. Okay, so to create a stump, okay, we are going to consider three dimensions. The first dimension is chest pain, blocked arteries, and the patient weight. Um, so how do we decide which variable which has to be coming as node? That is decided by creating the uh, that or creating different possibilities with the dimension, or creating the by calculating the information gain. That is how you decide the node, the best node for that particular stump, for the initial stump, I would say. Okay, and now, as I told you, each record will have the same weightage. So the same weightage means, here how many records we do have? We have 8 records. 1, 2, 3, 4, 5, 6, 7, 8. So the weight for each record is 1 by 8, right? So everything will have the equal weight. The total weight should be equal to 1 for mathematical simplicity. So we give the weightage of 1 by 8 for every record. Okay. However, as I told you, however, after we make the first term, these weights will change in order to guide in order to guide how the next term is created. So for initial weights are 1 by 8, each record has got the same weight, but when we construct the second term stump, these weights will change. Why these weights will change? Because the wrongly predicted um, records by the first stump will be given higher weightage in the second stage, right? That is the reason why the weights will change in the second iteration. You will understand that shortly. But the first takeaway here is we need to create our first stump. To create our first stump, what we have to do is we have to assign the same weight, same sample weight for all the records. Um, Okay, and now how do we construct this term? We use the same techniques that we have that are described in the we use the same techniques. Uh, we use the same techniques described in the decision trees. In the decision tree, how we have done the split, the best split is determined by calculating the information gain, right? So the similar way here, the best split is decided by calculating the information gain only. So you will see that shortly in the next slide. So if you look at this, so based on the chest pain, if I take the dimension of the chest pain, so how many are like chest pain is S or no, right? If the chest pain is S, there are like 5 records are rightly classified, right? So if it's chest pain is S, that means 5 records are S. That means chest pain is S means so we yes heart disease. So in the S, how many are there? Let's suppose if I'm considering chest pain as S and heart disease as S, if you look at this S and S, this is S, S. This is S, no. This is S, no. So when we say chest pain is S, and when we are constructing a stump saying like chest pain as S, but heart disease is S, in that case is 1, 2, 3 cases. But in 2 cases, we are wrongly predicting this particular value, right? When I'm constructing a stump something like this. I'm saying like when chest pain is equal to S, when chest pain is equal to S, I'm saying heart disease is equal to S. If chest pain is equal to no, I'm saying heart is equal to no. This is my first stump. Okay. In this case, when I'm saying when chest pain is equal to S, I'm predicting that as when I'm predicting the patient has heart disease. But only out of 5 patients that I have that fall into this particular leaf, only 3 predictions are right, 2 predictions are wrong, right? So because only the patients, these 3 patients has heart disease, these 3 patients doesn't have heart disease, even though the chest pain is yes for them, heart disease is no. Okay, that is how you came up with this particular thing. So this is correct is yes and the incorrect is true. When chest pain is equal to no, when chest pain is equal to no, how many records are there? So I have 3 records with chest pain is equal to no. When chest pain is equal to no, we are saying no heart disease. But if you look at this, he has heart disease, yes, right? So this is wrongly predicted. These are rightly predicted. So that comes like 2, 1, right? That comes like 2, 1. So now we calculate the entropy. You already know how to calculate the entropies at different levels, and also you also know how to calculate the information gain. Information gain is nothing but the subtraction of entropy from the different levels. Okay, and now what you have to understand is you already learned this thing in the decision trees by getting different combinations out of the rows, right? As this is a categorical variable, so as this is a binary variable, there are only 2 possible combinations. If it is the patient's weight, you can come up with different ranges, right? Patient less than 180, patient greater than 210, something of that sort. We already discussed different methodologies for that. Okay, so we came up with something called as average of all of them 176, but you know the all that stuff that I don't want to actually repeat them, how to actually determine different possibilities of the dimension variables. Okay, so but the whole thing comes down to this one. if you look at this, information gain for this particular tree is 0.47, information gain for block data is coming as 0.5, whereas the information gain for weight greater than 176 is coming down to be 0.8. So when you have higher information gain, you will use that particular stump as the initial stump. Okay, that particular tree as the initial stump. So now we determine, so now we decided that this is the final, this is the first term that we want to go with because this has the highest information gain. Now the next thing that we want to calculate here is how much say this particular stump will have in the final classification. So that is the next step, right? So we came up with one stump and it made some predictions. How many predictions it has correctly done? It has correctly done 7 predictions. Okay, 7 are correctly done, are rightly predicted, whereas one particular record is wrongly predicted. Okay, from this you have to understand that in the next iteration this record should be getting more weightage. Okay, this record has to be getting more weightage. Okay, so we will discuss about how the weightage will get changed with the secondary, but now it is time to calculate what is the say that this particular record will, or particular this stump will get in the final classification, is what we're going to see now. So we use total error to determine the amount of say. Okay, first of all, to calculate the amount of say for this particular stump, we calculate the total error, and from the total error we calculate the amount of say. So once we know the total error, uh, to calculate the amount of say, this is the formula. So for now, don't bother about how we derived this formula. Just take my take this slide, or take it as granted for now. We will actually see the derivations of all this stuff shortly in the upcoming slides. But so to calculate the amount of say for any stump, we need to know total error. From the total error, we calculate the amount of say. Okay, so now you have to learn how to calculate the total error, right? So once you know the total error, it is just a mathematical calculation. Now, to calculate the total error, so you need to get away with this. So the only record that is wrongly classified is this particular record. So this record is wrongly classified. So weight is less than, uh, weight is 167 for this patient, right? So so when weight is greater than 176, okay, you're saying the patient has heart disease. Okay, and when weight is less than 176, you are saying that as no heart disease. Okay, this particular stump predicted this particular patient has no heart disease, but in real he has heart disease. Okay, so this is the only record where the error is made. If you take any other record, let's take 205. If weight is greater than 205, this stump predicted that as a heart disease as is, and the real the real observed data is also has heart disease, or the real patient also, the patient also has heart disease. If you take another record, 172, weight less than 172, weight 172 is less than 176, right? So the stump predicted this as no heart disease, and the real, in the reality as well, he doesn't have heart disease. So so everything is, all the records are rightly predicted. This is rightly predicted, rightly predicted. Every record is rightly predicted except this is wrongly predicted. Now to calculate the total error, we just need to sum the weights associated with the incorrectly classified samples. Okay, here there is only one record where it is incorrectly classified, right? Let's suppose if it incorrectly classified two records, these two records, let's suppose, yeah, then the total error will be the sum of all the weights, which is 1 by 8 plus 1 by 8, which will be 1 by 4. This will be the total error. Total error is nothing but the sum of weights associated with the incorrectly classified samples by that particular stump. Okay, so in this case, as we have only one stump, one record which are wrongly classified this particular stump, so total error would be 1 by 8. So now, one thing to understand here is the total weight of all the records is equal to 1. So total error can be in between 0 and 1. Okay, total error will always be in between 0 and 1. So if the total error is 0, that means the stump has done perfect classification. If the total is 1, that means every classification was done wrongly by the stump. Okay, that is what total error 1 means. If total error is equal to 1 means it is nothing but the summation of all this records, right? Summing up to 1. Weight is equal to 1, and if the total error is equal to weight, that means every record is wrongly classified by the stump. In that case, what should be the say amount of say for that particular stump? It should be very less, right? If the total error is low, it's something that can be I mean it's a simple thing. So if the total error is low, then that stump is working very good, and the stump is doing a great job, it should be given more weightage, right? When the total error is high, when the total error is high, the stump is not doing a great job in the classification. Stump is not doing a great job, right? In that case, amount of say has to be low for that particular stump. Okay, when total error is low, that means stump is doing a great job at classification, so amount of say has to be more for that particular stump, right? So now in this case, total error is equal to 1 by 8, and total error will always be in between 0 and 1. 0 will be for a perfect stump, and 1 for b 1 total error will be 1 for a horrible stump. Okay, now let's just look at this analysis now. Now if you look at this, so I have drawn a graph between amount of say and the total error. Okay, so if the total error is equal to 0, okay, before going there, let's just understand this particular analogy. No, never ever go to, let's understand 0 and 1 later, but let's take some sample example. Okay, uh, so if you look at this, now for a 0 and 1, this equation will freak out. That basically means as if you substitute total error as 1, what that will become log 0. Okay, and if you submit total error is equal to 0, that becomes log infinite, right? Log 0 is undefined. You don't have any value for log 0. So when total error is equal to 1, logarithm of 0 will become undefined, and when total error is equal to 0, it becomes log of infinity, so that diverges. Okay, so these are the two scenarios where the amount of say will freak out. But if you look at the other case, so amount of say, when the total error is low, amount of say is high, right? So if you look at this particular space, the amount of say is high in all the spaces. Slowly it came down to 0 at a particular point, and then then the amount of say is constantly decreasing, right? So when the total error is increasing, the amount of say is decreasing, but at some point amount of say is equal to 0. Okay, what does negative amount of say indicates? That's what you have to understand. You are seeing a negative uh, you know negative value for the amount of say, right? So if a particular stump is getting a negative amount of say, that means it, instead of saying, like, you can take it like this: if a stump votes for heart disease, the negative amount of say will turn the vote to not a heart disease. When we say amount of say is negative, that means total error is very high by that particular stump. That means it is wrongly predicting it's making a wrong prediction for every record that we pass. So when we reverse that, how do we understand the output of such a stump? You need to understand that particular such a stump as negative, right? The reverse prediction has to be made. Let's suppose I know a stump where total error is equal to 1 for this particular stump, and you are passing some data to this. The total error for this is 1. That means every prediction that it made will be wrong. That is what total error is equal to 1 means. 1 means, right? So now if I'm passing a record to this and it is saying the patient has heart disease, how do I need to convert this? I need to understand this as the patient don't have heart disease, right? Don't have heart disease is what I have to understand. Okay, that is what negative amount of say actually indicates. When there is a negative amount of say, that means the patient output or the prediction would be the reverse of the actual prediction made by this term. That is what negative amount of say actually means is. Okay, now if total error is equal to 1, this implies the classifier is completely wrong. Okay, making 1 minus total. We are understanding about the total error is equal to 1 case. When we say total error is equal to 1, that implies the classifier is doing completely wrong and the logarithm of 0 will be undefined. In this case, amount of say will be undefined. When total error is equal to 0, the classifier is doing a perfect job, and so this leads to infinity and logarithm of infinity diverges. Okay, when total error is equal to 0, the weak classifier is flawless and it should receive a very high weight. However, practically an adjustment is made to prevent division by 0. So if you look at this, so when total error is equal to 0, you need to that particular stump should have higher amount of say. But the mathematical equations are freaking out because you're getting infinity and the logarithm of infinity diverges, right? So to avoid these two errors, so this should get you know 0. When total error is equal to 1, that is the classifier is not at all doing good, it is doing completely wrong. In that case, the weight for that particular stump is meaningless, so we need to disregard that. To avoid these two cases, to avoid running into this undefined cases or divergence cases when total error is reached to 0 or 1, you're adding a small positive value to the total error. So this will eliminate us going to infinite or 0. Like now if you substitute 1 here, 1 minus 1 plus sigma by 1 plus sigma, which is a very small value. So this is not allowing or letting us go to 0 value, right? Logarithm of, we are getting logarithm of something. Similarly, if you are substituting total error is equal to 0, 1 minus 0 plus sigma by 0 plus sigma. So it is also not going, this is also not returning as infinity, so that logarithm will not diverge. So to avoid going to these two conditions, so the edge cases, we are adding just a small, positive value. To handle the edge cases where total is equal to 0 or 1, we add a small positive value sigma to avoid division by 0 or the logarithmic divergence. So now that final formula for amount of say is 1 by 2 into logarithm of 1 minus total error plus sigma by total error plus sigma. Total error is nothing but the summation of all the weights of the records which are wrongly classified or which are predicted wrongly. So we also understand the graph between amount of say and the total error. So when the amount of say is negative, that means you need to understand the output of that particular stump in the other way. Okay, if it is heart disease, you need to understand that as not don't have heart disease. So that is all about amount of say, calculating the total error and all that stuff. Okay, let's take another example. I already explain this to you. Let's suppose if the total error here is if you take this chest pain, if you're predicting, you already understood this, right? If chest pain is equal to yes, the stump is saying the patient has heart disease. But not all the patients have heart disease. Two patients do not have the heart disease even though the chest pain is yes. So these are wrongly predicted by this particular stump. And if the patient don't have chest pain, we are predicting that as do not have heart disease, but this particular patient has the heart disease. So what is the total error made by this particular stump? Total error is summation of all these weights, which is 1 by 8 plus 1 by 8 plus 1 by 8, which is 3 by 8. So total error for the chest pain is 3 by 8. To calculate the amount of say, you just have to do 1 by 2 logarithm of 1 minus total error by total error. So this value will give you the amount of say. So this is just an example of calculating the amount of say for a for this particular case. If you're considering this as the initial stamp, okay. If chest pain has the highest information gain, we will consider this as initial stamp. If this is considered as an initial stamp, then the total error is calculated this way and the amount of say is calculated this way. Okay. Um, and now going back to the second step. The second step is now you have to update the sample weights based on the errors made by the first term. right? So we created the first stump, we got the first stump, and now we are ready with the first stump, and we also got what is the amount of say for the first stump. Now we are going ahead and moving to construct the second stump. As I told you earlier, in the real world, for any such kind of data, we will create around 100 such stumps to do the final classification. Okay. Now, as I told you, this particular stump is wrongly predicted by our initial stump. Now, you have to give the higher weightage for this particular stump. Okay. Um, so what does that actually means is giving the higher weightage for your wrongly classified record actually means is that it is nothing but emphasizing the need for the next term to correctly classify by increasing its sample weight. So increasing it weight, what does that means is the first term has done very good with all the other records except this particular record. Now we need to emphasize that the second stump has higher responsibility in rightly classifying these kind of records. Okay, that is nothing but that is all about increasing the sample weight for this particular record. So this is calculated by using the formula. This is the new sample weight for a wrongly classified record. Okay, this is wrongly classified record. For such records, sample weight is calculated by using the formula. So new sample weight for a wrongly classified record is sample weight, the previous sample weight into e to the power of amount of say. So this is the new sample weight for the incorrectly classified records in AdaBoost. Okay, so the new sample weight is calculated by using the existing sample weight multiplied by e to the power of amount of say. What is amount of say? Amount of say is nothing but the amount of say of the stump which has wrongly classified that particular record. Okay, right. So now look at this. This is the graph between amount of say and e to the power of amount of say. Okay. So when amount of say is low, e to the power of amount of say is also low. When amount of say is high, e to the power of amount of say is also high. Okay. So now how do we calculate the amount of say? So the new sample weight will be equal to the existing sample weight, which is 1 by 8 into e to the power of amount of say, right? So this is what we have written the graph, e to the power of amount of say into amount of say. So if you carefully understand the two cases that are possible with this, let's take back the first term. If the first term has done a great job, okay, if the first term has done a great job. How what indicates that? Amount of say actually indicates that, right? If the amount of say is high, that means total error is low, right? That is what you understand from this graph. When the amount of say is high, the total error is low. That means the stump is doing a great job. When the amount of say is low, that means total error is high. When the total error is high, that means the stump is not doing a great job. When the amount of say is high, that e to the power of amount of say is also high. That means the new weight will be much higher than the original weight, right? When this is a very high value, the new weight will obviously will be a higher value. Okay, so that is what it says. When the amount of say is relatively large, the last term did a good job classifying samples. Then we will scale the previous sample weight with a large number. This means the new sample weight will be much larger than the old one. When the first stump is doing a great job, the weightage for the wrongly classified sample will be very high. Okay, that makes sense, right? So we need to increase the weight to a drastically because that is the only sample which there are very few samples. The stump is doing a great job, but it is not good, doing great job with some samples. So we need to increase the weight of the samples to ensure or to emphasize the next stump to make the right predictions or to the importance of the next stump to emphasize the importance of the next stump to rightly classify such records. Similarly, when the amount of say is low, that means the sump is not really doing a great job. In that case, the sample weight, when this is low, the new sample weight will also be little, will not drastically change, right? Then the previous sample weight is scaled by relatively small number. That means we are multiplying with a very small number. That means the new sample weight will only be a little larger than the old one. Okay, the new sample weight will be a little larger than the old one because the stump is not doing much great job. There will be so many records which are wrongly classified. So the importance for one record will not drastically change. It will be it would be even across all the records because there are so many records which are wrongly classified. That is what it emphasizes. This graph actually emphasizes. So when the stump's amount of say is high, e to the power of amount say is high, so the new sample weight will be high for the record. Whereas when the amount of say is low, that means the stump is not doing a great job. And the stump is not doing a great job, the new weight will be little larger than the older weight for a wrongly classified samples. Okay, so that is the simple thing to understand from that particular thing. And now, um, what is the weight for the rightly classified new sample weight for the rightly classified samples? Okay, so the for the rightly classified samples, so if you take this particular stump, it has done the great job with all these records. Out of 8 records, it rightly classified 7 records. So what will be the new sample weight for these weights? So in the when you're for the second term, the importance for these records should be decreased, right? The importance for these records should be decreased in the sense the sample weight for these records has to be decreased. So the new weight for the rightly classified samples is equal to sample weight into e to the power of minus amount of say. Okay. So for misclassified, it is sample weight into e to the power of minus amount of say. This is for wrongly classified records. For rightly classified records, for the right classifications, new weights is equal to sample weight into, sorry, this is plus, right? E to the power of, for wrongly classified, it is e to the power of amount of say. For the right classifications, it is e to the power of minus um, amount of say. So that is the only difference, plus and minus. Now let's understand how does this e to the power of minus amount of say looks in the graph when drafted with amount of say. Okay, um, where is I do have that or not? Sorry. It's a vice versa, right? It looks completely reverse. Okay, it's just the reverse of this particular graph, and the amount of say is this would looks something like this: e to the power of minus amount of say. That means when the amount of say is low, the weight will be higher. The e to the power of minus amount of say is higher. That means, so the new sample weight would be equal to sample weight into e to the power of minus amount of say. That means when the amount of say is low, when the amount of say is low, e to the power of minus amount of say is higher. When this is higher, this will be higher. So for rightly classified, when the amount of say is higher, the new sample weight will be much higher for the rightly classified. But when the amount of say is low, that means the stump is not doing such great job. So in that case, new sample weights will be higher than the original sample weights for the rightly classified ones. Okay, because there will be very lower number of records. Similarly, these two conditions will get reversed with e to the power of minus amount of say. Okay, so now if you look at this, if you calculate the new weights, um, if you calculate the new weights for each of the records, this is a rightly classified one, so this becomes 1 to the power of 8 into e to the power of minus amount of say. Okay, amount of say would come something like this. If you want to calculate or do the math, the right math, so what does it will be? Amount of say for this term is 1 by 2 log of, so amount of say for this will be 1 by 2 log of 1 minus total error is 1 by 8 by total error is 1 by 8. So 1 by 2 log 1 minus 1 by 8 will be 7 by 8 by 1 by 8. So this becomes 1 by 2 log 7. So amount, it comes down to some value, and if you calculate that particular value, you get this new weight. Okay. Similarly, um, for the wrongly classified one, it will be higher weight. That means e to the 1 by 8 e to the power of plus as, right? So when you calculate this particular value, you will get this particular weight 0.33. Now if you look at this, the wrongly classified record has higher weightage, higher new weight. Okay, so that's how you calculate these new weights. But you have to normalize them. If you calculate the sum of all these weights now, it comes down to 0.68, but you want the total weight to be equal to 1. So for that, what you have to do, you just have to divide every record with 0.68. So these are the normalized weights. These are the new weights calculated, and these are the normalized weights. That means total weight for these is 1. Total weight for these is 0.68. So you want the total weight to be 1. Okay. For easier mathematical calculations, so and to be consistent, so you normalize that, so that new weights will become this one. These are the new normalized weights. So if you look at this record has highest weightage. The wrongly classified record has got higher weightage now when compared to the rightly classified records. Rightly classified records just got the new weight as 0.07, whereas wrongly classified record has new weight as 0.49. So this emphasizes that second stump has higher responsibility of rightly classifying this particular record. How does that, how are we emphasizing that is what we are going to see now. Okay. Now, how are we emphasizing? Using the normalized weight to make the second stump. Now, we use these new normalized weights. Initial weights are 1 by 8, 1 by 8, 1 by 8, right? Now, the new weights became like this, or looking like this, where we are highly emphasizing the wrongly classified sample. That is, so we are putting more emphasis on correctly classifying this sample. So the one that is misclassified by the first stump, we are putting more emphasis on the second stump to rightly classify this. Now we use the modified sample weights to make the second stump in the forest. Okay, so to create the second stump in the forest, we need to reconstruct this particular data. Okay, the data matrix has to be reconstructed such that this sample weight of 0.49 is reflected in this particular data. Right now, this data doesn't reflect this weightage. We just calculate the sample weight. Now, in the next step, what we do is we create a new data set altogether. Now, this record has 8 records. Okay, this data matrix has 8 records. We are creating a fresh table with 8 rows, or with weight records. Now, how do we make sure there is more emphasis on the wrongly classified record is something that we're going to see now. So what we do, we start by making a new empty data set that has the same size as the original one. Okay, we create a new data set whose size is same as the original data set. Okay, and we see where the number for now. How do we pick the how do we construct this new data matrix is that we pick a particular random number between 0 and 1. Okay, we pick a random number between 0 and 1, and we see where that number falls in the sample weight distribution, and accordingly we pick that particular record and place it in this data matrix. Okay, maybe don't get confused. Let's understand with a simple example. Now, what I have to do, I have to pick a random number between 0 and 1. So if I pick the number as 0.07, okay, if the number is between 0 and 0.07, okay, I'll place this record in this particular data set. Okay, if my if the random number that I have picked, again, let's suppose, um, um, uh, again pick a random number. If that random number falls in between 0.07 and 0.14. Okay, so from 0.07 to 0.07, we place this record. If it is between 0.07 and 0.14, the summation of both these records, if the random value that we picked is between these two values, we put this particular record. Similarly, if you go here, so it comes down to 0.14 to 0.21. If the random number that we picked is between these two numbers, okay, then we put this sample in the record. If you look at this now, we are improving the weightage for this. If the number is anywhere between 0.21 to 0.70, look at the range of this particular record. It is too high, right? That is how we emphasizing the more weightage for this particular record. Every time you pick a value, you pick a random value, so the probability of falling in this range is more because this range is very high when compared to any other ranges, right? So again, this goes to 0.70 to 0.77 for this, 0.77 to 0.84 for this, so 0.84 to 0.91 for this, so 0.912, somewhere around 0.9 and something, like 1, 0 point somewhere like 1. Okay. Sorry, I have to improve this 0.78. Yeah, somewhere around between this. If it is 0.77 also, we'll place this. So everywhere you will get one incremented. So that comes down to 1 here finally. But the main idea behind this is simple. So if you look at this, the range here is very high. The distribution here is very high. So the probability of the randomly picked number falling in this region is very high. So when the randomly picked number falls in this range, we will place this particular record in the new data set. Okay, understood? That is how we are constructing a new data matrix of the whose size is same as the original data set. Okay, here you in the original data set you have 8 records, so in the new data set also you will get 8 records. Based on the sample weights distribution, you pick a random number. If the random number falls in that particular range, you will place that particular record in that new data set. Okay, so this is how it actually works. So then based on the sample weights distribution, we picked different random numbers and then we constructed the new data matrix. Okay, so the new data matrix looks something like this. And if you look at this row repeated 4 times. Okay, whereas you got some rows, some other rows 4 times. You might have some missing records. You will not see all the records coming over here. You will see, but you will see more number of records which are misclassified by the first term. This is how you are increasing the weight of that wrongly classified, or you're emphasizing the importance for that wrongly classified record. Ultimately, this sample was added to the new collection of sample 4 times, reflecting its larger weight. Okay, the larger weight means the range of that the range of that particular record in the sample weights distribution is higher. So the probability of a randomly picked number falling in that range will be higher. So you will see that record coming up multiple times in the newly constructed data set. Okay. So that is how you're emphasizing the importance of that particular record. Now you will feed this particular data matrix. You will feed this particular data matrix to the second stump, or you will construct a new stump of from this particular record. Again, going back here, um, lastly, we give all the sample weights equal weights just like before. Now you got the new data matrix, right? In this data matrix, you got the wrongly classified record reflected multiple number of times. So now when you're doing, it's again like a fresh data matrix again, fresh data. So the sample weights. So now you will give the same importance for every record now, because you already reflected the importance of wrongly classified record by doing that sample weights distribution and picking a random number between 0 and 1, right? So you reset the sample weights to 1 by 8, which emphasizes that every record has the sample weight. So now it's just like all these records has the there are multiple records. So there will be a larger penalty if they are being misclassified. So as these are all same records in the learning process, that particular model will try to emphasize more importance to rightly classifying these records. Or if it wrongly classifies, it has higher impact on its accuracy, right? So now again, you go back to the beginning and try finding the stump that does the best job. It's the similar process again. You again come up with different combinations using the dimensions that are given, and you will calculate the information gains, and again you will come up with some stump. Okay, so it can be any stump again. So it's again coming back to the old state, but with a new data matrix. So this is how the errors made from the first tree influences how the second tree is made. So now if you clearly understand, the second stump is influenced by the output or the predictions made by the first stump. The predictions, the wrongly predicted values by the first stump will get more emphasis um, in the second stump classification. Similarly, you will keep on going constructing different stumps. Okay. And the final step is using stumps to make classifications. Now, finally, you have created a number of stumps. Technically, in the real world, you will create around 100 stumps to do the classification, right? But now, at the end, how do you make the classifications out of all these stumps? You will do it this way. Okay. So now, if you look at this, I have created six different stumps. Okay. Three stumps, four stumps. Like now I have the new data set. Okay, now I have a new data. um, I have a new data given with all the rows: chest pain, what are the other two rows, blocked arteries and patient weights, blocked arteries and patient weights. Okay, I have this record given to me. Now I fed this record, I mean, uh, I fed this record to this particular stump, and this particular stump, this particular stump, this particular stump, and all these four stumps says this patient has heart disease, and these two stumps says this patients do not have heart disease. And now I'll sum up all the amount of says of all these stumps. So that sums down to 2.7. 2.7 is the amount of say for all the stumps which says this patient has heart disease, and 1.23 is the amount of say by the stumps which decided these patients do not have heart disease. As the summation of all of these stumps is higher than the summation of these stumps, we say this patient has heart disease. This patient has heart disease. It's simply something like this. Let's suppose if you take the other case, let's just for your example. Okay, if let's suppose if all these stumps said the patients do not have heart disease, these two some stumps said the patient has heart disease. Okay, now the summation of the amount of says of the stumps which said heart disease is 0.73. If you will calculate this value of this one which says heart disease, do not have heart disease, is the you'll just calculate the summation of all the stumps. This is 0.32 plus 0.78 plus 0.41 plus 0.82. So ultimately you find out the value of this. Let's suppose this is x and this is y. As you find x is greater than y, you classify that patient do not have heart disease as the amount of say for the amount of say of the stumps which misclassified or which classified the patient do not have heart disease is higher than the amount of say of the summation of amount of says of stumps which classified that patient has heart disease. As x is greater than y, we classify that patient has heart disease or not a heart disease. That is how you make the classifications using the stumps at the end. So to revisit the ADA boost, what you have done, you started by creating a single stump by considering all the sample weights as 1 by 8, and then you calculated the total error for that particular stump, and then you calculated the amount of say. With that, it is done. The first stump is ready. Now you calculated the new sample weights by using the formulas. Sample weight, new sample weight is equal to sample weight into e to the power of amount of say for misclassified records or misclassified samples, and new weight is equal to sample weight into e to the power of minus amount of say for the rightly classified samples. So that way you calculated the new sample weights, and then you normalized the sample weights, right? You normalized the sample weights, and using the normalized sample weights, you constructed the second stump. The first step is you using the sample weights, normalized sample weights, you created a new data matrix. um, you created in sorry you created a new data matrix. The new data matrix is created by the new data matrix size will be same as the original data matrix, but the only thing is you pick some random value, and based on the sample distribution of the sample weights, you construct this particular data matrix. So the as the probability of a random number you picked will be higher for the misclassified samples, so there is a high probability that the random number will fall in this particular distribution. So there is a high probability that that particular record will repeated multiple times. That actually happens in the real world, right? So as the bandwidth is high for the wrongly classified samples, you will get that record more number of times. That is how you emphasize the importance of that particular record, rightly classifying that record. Again, you reset the sample weights, and again you construct a new stump by just using the information gain formulas and entropies formulas. It's just a simple thing. So you again do construct a new stump, so you will have the new stump ready, and it has its own uh, amount of say, right? So now similarly you will construct n number of stumps, and you will have the amount of say for all such stumps. Again, when you get a new record, you will pass that to all the stumps, and you take the output of all the stumps. And when if it is a binary classification, you say you calculate the summation of all the stumps which said as S, and you calculate the summation of all the stumps which said no, and compare the amount of says which said S and no, and whichever has the highest amount of say, the new record will fall into that particular category. So that is how the boosting technique actually works, and the ADA boost is one such algorithm. Um, okay, is this clear?
Yes. Yes.
Yeah. So I think let's pause for 10 minutes, and then we will look at gradient boosting. So I'll end the session today with gradient boosting. So gradient boosting for regression and classification, there are two things. So with that, we will be done with boosting. So I'll continue after 10 minutes. So now we will talk about the gradient boosting. So gradient boosting, this technique is used for regression as well as for classification. So now I hope you already know about what does regression and what does classification means is. So just to rewind, I mean just to repeat, regression is something where the predicted value would be a continuous value. Okay, if you look at this example here, we are trying to predict the weight of a particular person. So this will be a continuous value, right? It can be anything between somewhere around 40 to 150. It can be any value, right? It can be 76, 75, 72, whatever it is. So when we are trying to find out such continuous values as an output, as the output label, we call that as a regression case. What does classification means is, classification is a simple one. So we say whether it is a spam email or not a spam email, whether it is a dog or not dog. Such kind of things are called as classifications. So now let's start by talking about regression case. So in this case, we are using gradient boost for regression. When we say regression, we are trying to predict a continuous value, right? So that is why we call that as gradient boost for regression. So when gradient boost is used to predict a continuous value, so like weight, we say that we are using gradient boost for regression. Okay, so the first step in the gradient boost is, whether it is for regression or classification, we create a single leaf. Okay, we start by creating a single leaf, and that single leaf, instead of creating a tree or stump, we start by creating a single leaf. So this single leaf is the initial guess for the weights of the samples. So if you take this particular case, we come up with one single value, which would be the value of weight for all the samples. Okay, we find out a value. That value will be the value of weight for all the samples. Okay, so that is what coming up with a single leaf means. Okay, so So most probably, okay, what would be the single value that represents all these samples? The single value would be nothing but the average weight, right? So average weight would be the, if you want to represent all these samples with a single value, that would most probably be the average value or the mean value, right? Central tendency, we talked about the central tendency already. We understood what is central tendency and all that stuff. So mean is the most uh, is the single value representation of this particular distribution, or for this particular weight distribution. So that would be the when in the gradient boost, the first step is to construct a leaf, and that leaf should represent all the samples. Okay, so that leaf would be nothing but the average weight. If it is for regression, the first step would be finding out the average of all the values in the label, and we use that as the first guess. Okay, so we predict that as the continuous value like weight. So the first step in gradient boost is to construct a single leaf that represents all the values. If it is for regression, that single leaf would be the first single leaf would be the average of all the values. Okay, right. So the first leaf would be the single leaf, and that would be just the average value for all the weights. So like ADA boost, this tree is based on the errors made by the previous tree. In any of the boosting techniques, it is always the same technique. So we give more emphasis on the wrongly predicted values by the first stump when we are constructing the second stump. Okay. Mm, that is the first thing. So it's a known step in ADA boost, like ADA boost, the um, you know, uh, higher weight. Like ADA boost, this tree is based on the errors made by the previous tree. But unlike ADA boost, this tree is larger than stump. Okay, this tree is larger than stump. In ADA boost, you will always create stumps, but in in gradient boost, you will construct trees larger than stumps, but there is a restriction. Gradient boost still restricts the size of tree. It is not like decision trees. You will not construct full size trees. There will be a restriction on the number of leaves in gradient boost. So it's unlike ADA boost. ADA boost relies on only stumps where it will have one node and two leaves. Unlike ADA boost, it will construct larger trees, but there is a constraint on the number of leaves in the gradient boost. So the gradient boost trees are made in between the decision tree and the ADA boost stump. Okay, there will be a restriction on the number of leaves that you construct in the gradient boost. So this is what it says. Unlike like like ADA boost, gradient boost builds fixed size trees based on the previous tree's errors, but ADA boost each tree can be larger than a stump. Like ADA boost, gradient boost scales the trees. However, gradient boost scales all the trees by the same amount. Okay. Mm, you will understand this shortly. This statement, gradient boost, also like ADA boost, gradient boost scales the trees. ADA boost scales the trees, right? That is amount of say. Amount of say decides the scale of a particular tree in the ADA boost, whereas in the gradient boost also scales. Gradient boost scales the trees. However, gradient boost scales all the trees by the same amount. Gradient boost scales all the trees by the same amount. You will understand this shortly when you look at an example. I'll show you. This is called as learning rate and gradient boost. You will actually see that shortly. Okay. Uh, so um, So in this example, like in the coming example that we are going to see, we restrict the number of leaves to just four. Okay, we will make sure the tree doesn't have more than four leaves. Okay, when we get four leaves, we just restrict the tree there. That is how we actually do it. Um, so in this example, we are just setting the leaves to be four, but in the real world, the number of leaves will be set to somewhere in between 8 to 32, depending on the case. Okay. In practice, people often set the maximum number of leaves to be 8 to 32, in between 8 to 32. So there is a restriction, but it would be in between 8 to 32, but in this case we are restricting the number of leaves to be just 4. Okay, so gradient boost we are restricting the number of leaves. That is what you have to actually understand. Okay, all right. uh, Now going back to the next slide. Look at this. So now the first step would be finding out the average weight. So the average weight for all these values is 71.2. So this is the initial leaf for us. And in the second leaf, what we do is in the second leaf, when we construct the second tree, um, so after constructing the initial leaf, which is the average weight, the next step is to build the tree based on the errors made by the first tree. Okay, the second tree will be constructed based on the errors made by the first tree. So you need to have some sort of weighting on the samples, right? Um, Okay, so now if you look at this, these are the weights. These are the actual weights for different persons, and this is the predicted weight by the first leaf, right? So this observed weight, the difference is called as the residual. So that is how the actual value is differing from the initial weight, right? So that is the error that we want to minimize. So now it is 88. We predicted that as 71.2. As we keep on constructing trees, we need to minimize that difference. So at some point, we should be able to predict the value of this particular patient as somewhere close to 88. But right now, 71.2 is the prediction that we made for all the samples by using just the first leaf. For all the persons, we predicted the average weight as the weight as 71.2, and there is a higher difference from 88. The actual weight is 88 and the predicted is 71.2, which is very far. As we keep on constructing the trees, we see this is getting reduced. Okay, how this will get reduced is something you will shortly notice, but that is our goal. You need to, when you keep on constructing multiple gradient boost trees, and when you append all of them, this difference should get reduced. The error that the previous tree made, or the difference between the observed weights and the predicted weight. What is the error of this particular patient? The actual weight of this patient is 88 and the predicted value is 71.2. That is called the error, right? And we also call that as residuals. So the next step is, the first step is to come up with a single leaf. That single leaf would nothing but the average value of all the labels. Here the label is the weight. So we come up with the average value as the first leaf. And the second step is you calculate the residuals. Residuals are nothing but the difference between the observed and the actual values, or the predicted values. So the actual value is 88 and the predicted value is 71.2. So the residual would be 16.8. Okay, we call that as pseudo residual. Now we calculate the residuals of all the samples. So once we calculated all the residuals, so these are the residuals we came up with. Okay, look at this. 56 is the actual. We predicted that as 71.2. That becomes minus 15.2. Now the next step is we construct the tree using these variables and the residuals. Okay, instead of the actual weights, now we use the residuals to construct the tree. Okay, the residuals are the errors made by the first tree. Okay, so now we come up with a tree. Now we build a tree using these dimensions and to predict the residuals. So now in the leaves we will have the residuals. Now you construct a decision tree using the entropies or whatever it is. You will just use the entropy information gains, and you come up with a tree. But what is the only difference between the decision tree and this tree is we are restricting the number of leaves to be 4. Okay, once we got 4 leaves, we are just restricting them, right? Remember, in this example we are only allowing up to 4 leaves. In this we are only allowing 4 leaves. But in the larger data sets, you will allow the leaves to grow up to 8 to 32. That is a different case. But in this example, we are only allowing 4 leaves to be happening. So once you reach to that particular, once you have that 4 leaves, you will consolidate the records coming up to the same leaf. Okay. So now the second step, what you do, you calculate the residuals and you construct the tree to predict the residuals by using the dimensions. Now we use these dimensions and you're predicting the residuals. So the residuals will fall as the leaves. And as we are restricted the number of leaves to be 4, so you are just stopping the tree growth here. Okay. Now, now the next step, what we do is we replace the residuals with their average. When multiple records uh, are coming down to one stage. If you look at this, these two records are coming to this particular leaf. Okay, and what you do is you just instead of you come up with the average of these two records. Okay, that will be the value of that particular leaf. So similarly for this leaf, you take the average of these two values. The residuals are coming up here. So if you want to understand this in much better way, take this example. So this particular person, okay, sorry, this particular person, this particular person has one has you consider the male, the gender is male, so gender is female, so this is false. So we come here, color is blue or not, color is red here, so color is not blue, so this is true, so we fall here. So the residual of this is 1.8. We are ending up here because we are just restricting the leaves. This is one leaf, one leaf, one leaf, one leaf, so we got 4 leaves, so we stopped here. Now, if you take the other case, male, so it comes here. It's not blue, come here. So 5.8 also. These two residuals are falling here. Now, we need to represent each leaf with only one value. So you take the average of both the values and get a value for this particular leaf. Similarly, you take the average of these two leaves and you come up with a single value, and that becomes the value of that particular leaf. That is how once you constructed the tree, once you constructed that particular tree, you take the average of both the values and you replace that particular leaf with that particular value. So you'll shortly see why we are taking the average of these values and all that stuff shortly. But understand right from now, when multiple records or multiple residuals are falling at the same node, we take the average of all those nodes. If it has 3 values, you take the summation of all the 3 by the number of residuals in that particular leaf, and you replace that particular leaf with that average value. So now you got that particular tree constructed. Now this is the average weight, this is the initial prediction that we have made, which is the leaf, and this is the new tree that we have constructed by using the residuals, right? Now if you want to make a new prediction, now you again take the first record. Initial prediction for this record is 71.2, right? When we didn't constructed this, what we have said, as we keep on growing the number of trees by constructing the number of trees, what we do is we need to reduce the difference between these two values. So that's what it's going to happen now. If you look at this, for this particular record, initial weight is 71.2 plus gender is female. It's false, so it comes here. And what is the color is not blue, which is false. Color is not blue is said, it is false, right? So color is blue, so the value of this is 16.8. Now 71.2 by the first leaf node, and 16.8 is a value given by the second tree that we have constructed by using the residuals. So the total predicted weight came to be 88. So we are, by just constructing the first tree, we are drastically reducing the difference between the actual and the predicted, right? So now 88 is matching 88. Is this a good model? Now do we stop here? No. So this is called as overfitting, right? We are exactly predicting the value of it. So this is called as overfitting, model overfitting. This, when you have higher overfitting models, it works perfectly on the training data, but not on the test data set or on the new predictions. Okay. So you should never allow overfitting. You always want to make sure you have the, you know, uh, you have something to avoid the overfitting. So that is what you actually have to understand how you'll achieve that overfitting. Okay. So now if you look at this, I'm introducing something called as learning rate. Okay. So this, to avoid that overfitting, gradient boost deal such overfitting problems by introducing something called as learning rate to scale the contribution from the new tree. Okay, so now instead of just adding the average weight or the initial leaf node with this particular tree, in between we are introducing a learning rate. So learning rate is nothing but you are taking a small step towards the right prediction. That is what learning rate means. Learning rate will always be in between 0 and 1. So after introducing the learning rate, what will be the new predicted value? 71.2 plus 0.1 into 16.8. So 71.2 is the initial prediction. 16.28 is the prediction made by this particular secondary, made from the residuals calculated by using by using the errors made by the first leaf, and you are using an learning rate. So the next weight is 72.9. So if you look at this difference between 82 and 72.9, with learning rate set to 0.1, the new prediction isn't as good as it was before. It was not as good as 88, right? So 88 it will create overfitting problem. So it's not as good as the earlier prediction, but it reduced, but it is a little better than the prediction made with just original leaf. So the main goal for us is the initial prediction that we made with the average is 71.2. We need to reduce the difference between these two by constructing more and more number of trees by using the bagging technique that we have discussed. Now in the second, by after constructing the second tree, we reduce the difference. So now the new value is 72.9, which is much closer to 88 than 71.2. Okay, so we are making a better prediction than the original leaf, okay, which predicted that the sample weight would be 71.2. In the other words, scaling the tree by the learning rate results in smaller steps in the right direction. So learning rate means it avoids overfitting and it actually moves smaller steps towards the in the right direction. Empirical evidence shows that takes a lot of stall steps in the right direction results in better predictions with the testing data, that is lower variance. So moving lot of smaller steps towards the right value is much better than uh, overfitting, right? So this avoids lower variance. What is lower variance means? A higher variance means the model is overfitting, right? So right variance, it actually taking the small steps in the right direction will avoid that overfitting problem. Okay, so that's what you have seen here. Without a learning rate, it got the right value, and this is an overfitting problem. So it may do well on the learning rate on the training data set, but not on the test data set. If you look at this, by just introducing the learning factor, we are moving in the right direction in smaller steps. In the long run, that will give you the good results. Okay, so that is what learning rate means. Once that is done, again, what we do, we calculate the residuals again. With 71.2, these are the residuals. If you remember, these are the residuals that were calculated from the when you have only the single node. Okay, so we predicted those residuals. Now with this complete tree, right, with the first tree and the leaf node, these are the new residuals. Okay, if you look at this, the residuals are getting reduced everywhere. That means we have taken a single step in the right direction. Okay, now using the new residuals coming up from this particular, what are the new residuals? New residuals are nothing but the difference between the predicted value by using this complete tree and to the actual predicted value. Actual is 88 for the first record, and for this new record it is 72.9 or something, right? What is the predicted? 72.9. 88 minus 72.9 is nothing but the 15.1. That is what residual is after constructing the first tree. Now again we construct a new tree for finding out these residuals. Again, this would be the second tree. Okay, now again we come up with a new tree to predict these residuals, and these two residuals 12.7, 13 minus 13.7 fall at the single node. So we take the average of both of them. It comes down to minus 13.2, 1.4 and 5.4. These two falls under these two came and fall here in this particular reef. So you take the average of these two, it comes down to 3.4. So the new tree will be this one. Okay, this is the second tree constructed by taking the errors made by the previous tree. Residuals are nothing but the errors. Okay, now if you look at this, the total tree would look something like this. Now if you get any new record, if you get any new record, or you take the first record. So if you take the total, if you calculate the weight by using these three trees, it comes down to 71.2 by the leaf node, 16.8 by the first node multiplied by the learning rate, 15.1 by the second tree, and the learning rate is 0.1. So the total weight is predicted as 70.74.4, which is better than 72.9 made by one tree. That means again we take a smaller step towards the right direction. So this is much closer to 88, which is another small step closer to the observed weight. Okay. So that is how we are taking one small step towards the right direction. Okay, that learning rate actually does that. Again, after getting the second tree, we again calculate the new residuals. The new residuals are smaller than the previous residuals. That means we have taken another small step towards the right direction. Again, using these residuals, we again construct with one tree and we again made the prediction, and we keep on doing this process until the specified number of trees have reached or there is no much change in the residuals. So we have taken another small step towards making good predictions. Each time we add a tree, the predictions, the residuals getting smaller, and we keep making trees until we reach the maximum specified, or adding additional trees doesn't significantly reduce the size of the residuals. Okay, we keep making trees until we reach the maximum specified, or adding additional trees do not specifically reduce the size of the residuals. Okay, so we keep on doing this until we reach the maximum number of trees specified. We in real world we go up to 100 trees, somewhere around 100 trees. I have just shown you an example of two trees here. We go up to 100 trees, or else when the residuals are no more reducing, and when there is no much significant reduce in the in the residuals, we stop this process. Okay, so that is called that is what gradient boost for regression is. Okay, we started with average weight and then we calculated the residuals. Residuals is nothing but the difference between the observed and the actual. Okay, predicted and the or else okay, actual and the predicted. So and then we predict, we construct the tree by restricting the number of leaves, and we predict the residuals and we construct the new tree. We added a learning rate, and then we again calculate the residuals. At every step the residuals are getting reduced, and we keep on doing this process until we get the maximum number of, until we reach the maximum number of residuals. I mean maximum number of trees or the residuals haven't shown much reduction. Okay, so this is all about gradient boost for regression. Okay, we used different formulas here, right? What are the different formulas that we have used? This you have taken average here. When multiple records ended up in the same leaf, we take the average for this. Why we have taken the average for this is what we will see. How does that actually works in the real world? Why we are taking the average of them is something which you will see now. So the next thing what you see is we see the gradient boost for regression algorithm, the mathematical representation of this gradient boost algorithm of the gradient boost for regression. Okay, so it is quite simple. What we have learned, that this is just a mathematical representation of what we have learned so far. Okay, so the input for this gradient boost algorithm is data, so which is xi yi, from I is equal to 1 to n. What is the xi? Xi is a vector of the sample. Okay, so when you say xi, this is xi, this is xi, this is xi, x1, x2, x3. So this is the vector that that xi is talking about. Okay, x1, x2, x3. Xi refers to each row of measurement that we will use to predict the weight. And what is yi? Yi is the weights. Okay, the label or the predicted dimension, predicted value. So this is y1, y2, y3. That is I equal to 1 to n. Ya refers to the weight measurement for each person in the data set. That is what data xi ya I is equal to 1 to n means. So, and the other thing that is input is differentiable loss function. Okay, so what is a loss function? Uh, Loss function is just something that evaluates how well we can predict weight. Okay, loss function, you will understand loss function later, but loss function is just nothing but it evaluates how well we can predict weight. Okay, so loss function that we use for gradient boost is observed weight minus predicted weight whole square. Okay, 1 by 2 into observed weight minus predicted weight whole square. So when we take the derivative of this derivable loss function, when we take the derivation of this, you will get 2 and 2 will get cancelled, so that comes down to observed minus predicted value. That is what we're calling it as residuals, right? Residuals is nothing but observed minus predicted. So for gradient boost algorithm, loss function is 1 by 2 into observed minus predicted whole square. Okay, so yi, if you look at this particular function, yi is the observed values, f of x is the predicted values. So f of x is something what we will predict, and yi is the, as you already know, yi is the observed values. So how do we predict these values f of x? You already have seen that process, but mathematically you have to just see that. So the input is xi by a, given xi and yi is equal to 1 to n, and also differentiable loss function. You can even change the differential loss function, but for gradient boost algorithm, the loss function is 1 by 2 into observed minus predicted whole square. This is the differentiable loss function. And now if you go back to the step 1, initialize model with a constant value. Okay, step 1, what we do, we take the average of all the values, right? So that is this is just the representation of that. The initial value is arg minimum of I is equal to 1 to n loss function. Ya is the initial value, ya is the observed value, and gamma is the predicted value, right? F of x. Um, f of x, right? So that's what we have learned here. F of x is turned to gamma there. F of x is nothing but the function that gives the predicted values. F of x is the function that gives the predicted values. That's not the predicted value directly, function that gives the predicted value. So gamma is that particular function. Now what is the loss function here? Loss function is nothing but 1 by 2 into predicted, so observed minus predicted whole square, right? This is the loss function. Now I'm taking that particular loss function and doing the summation for all the samples. Now I have 3 samples. 1 by 2 into predicted is 88 minus predicted whole square. Now we want to find out the predicted value only, right? Uh, so we want to find out f naught of x, the function that gives the um, smaller predicted value, that gives the predicted value. So we are trying to find out that initiate the model with that constant value. So I'm expanding this loss function now. So 1 by 8 into 88 minus prediction whole square plus 1 by 2 into 76 minus predicted whole square plus 1 by 2 into 56 minus predicted whole square. Now when you want to predict a value for this, you want to come up with a single value for this. You're trying to find out the one value. You want to represent all these records with one single value. So how do you do that? Yeah, you do that by finding out the minimal value of the loss function. Okay, loss function is nothing but 1 by 2 into observed minus predicted whole square. Loss function has 2 parameters. One is predicted and the other one is function that predicts the lower value. Okay, so now this is the predicted value. Now we are trying to find out this particular value. Now what do you do to find out the minimum value? You take the derivative of this and equate that to 0. So now I have taken the derivative of this. Derivative of this is nothing but 2 and 2 will get cancelled. So this into minus 1, because we are differentiating that with the predicted value, which is gamma, right? So that minus is coming before, minus coming before. So now you do the summation of all of this and equate that to 0. So now the predicted value is coming down to the average of all these values, right? So the average of all these values. So we end up that average of the observed weights will be the value that we initiate the model with. That is a leaf value that we have created. So in gradient boost, the first step is initial, you pass the input as input, which is the data matrix, and the law you use some loss function, and then the first step is to find out the initial value of the leaf node. To prove the initial value of the leaf node is nothing but the average of all the values. When you learn the algorithm, you found out that it is just the average or average value that is the best representation of all these values, right? So you have just done the mathematical proof for that. What you have done, you have expanded the loss function and then take the derivative of that loss function using the predicted, and you calculated the predicted value. That predicted value is nothing but the average of all the weight values. Okay. Now the first step is done. What is the first step? The first step is the initiating the predicting value with the average value. The first step is done. The next step is, what is the next step? In the next step, you have calculated the residuals, right? And that is what you have done. So now let's understand this algorithm. This is the step two. Now you have understood what is input and what is step one. Now we are trying to understand the step two of this algorithm. In the step two, the first thing is m is equal to 1 to capital M. Small m indicates the current tree. M is nothing but capital M is nothing but the number of iterations or number of trees that you want to connect. That you want to construct. So this is just a iteration in the for loop is just an iteration from 1 to m. So you will repeat, if you want to construct 100 trees, you will repeat all these steps for 100 trees. Okay. So now let's understand this particular step. In generic terms, you will make m trees. M can be 100 in the real world, but in practice, most people set m is equal to 100 and make 100 trees. That is what actually this means. Now let's understand this particular step, calculating the residuals. Okay. Now, uh, you look at this derivating with respect to f of xi. That means derivating with respect to the predicted. Okay, the function that predicts the that find out the predicted value. So f of x is nothing but the predicted, and the loss function is 1 by 2 into observed minus predicted whole square. This derivative is nothing but this one. And when you do the derivation for this, you get observed minus predicted, and do them, and you get a minus before this, right? Because you're derivating with respect to predicted. So at the end, when you apply the chain rule, this 2 will come forward, 2 and 2 will get cancelled. So to say you that 1 by 2 into 2 into observed minus predicted into, when you're taking the derivative with respect to predicted, you get minus 1. So 2 and 2 will get cancelled. So the minus 1 will be before, you will get observed minus predicted. Okay. So now that's what it comes down to. Okay. Now let me show you what does this actually means is. This is now you understand this derivative. What is this f of x is equal to f of x minus 1? M is the previous tree, right? Since now we are at m is equal to 1. Okay. 1 minus 1 is equal to 0. When you're constructing the first tree, m would be equal to 0. Okay. That means since m is equal to 1, that means we plug f naught of x in f of m minus 1 x. So f of x is nothing but, so the predicted value, which is f of x, is nothing but the previous predicted value. Okay. Here f of x is nothing but, so predicted is nothing but f of x, that we have understood, right? Predicted is nothing but the f of x. So this predicted, in place of f of x, we are replacing the previous tree's value, m minus 1. So we replace predicted with f naught of x. So that is what this equation actually means is. Okay. Now, what you're simply doing, derivative of the loss function and replacing the predicted value with the previous tree's predicted values. Okay. So that is what actually that means. Now coming back to the next step, once you have that predicted value, once you got that residuals, calculated the residuals of all of them, for the first tree from I equal to 1 to n. Okay. How do you represent them? R21, R11, R12, right? Like if in this example, let's suppose if you have just only 2 leaves, so this would become R11 residual of 1, R21, R residual of 2, 1. Now look at this, fit a regression tree to the RIM residuals that we calculate. So once you calculated the residuals, which is nothing but the observed minus predicted difference, that's how we calculated the residuals, right? So just remember this. If you are clear with this algorithm, it would be easy. How did we calculated these residuals in the first step? We calculated these residuals by taking this actual value and the predicted value from the previous tree, right? That is what it is. And the next step, the actual value minus predicted value by the whole trees, f of f minus 1, right? So that is what it actually means is, when it comes to the next tree, it will be just the previous tree f naught of x. Okay. the residual of the previous tree. The predicted predictions made by the trees up to that point. All right. Where are we? Okay, we are here. So now we do this the next step is fit a regression tree to the RIM values. So we predict the residuals. You construct a regression tree that fits the residuals. So leaves are the terminal regions. This little m is the index of the tree. So you're talking about RJM, right? M is the index of tree. Now we are at tree number 1. So M will be 1. J is the number of residual. Okay. Little j is the index of the leaf in the tree. Okay. Leaf index. So this is first leaf. This is second leaf. So this is how you need to understand the residuals. Now once we got the residuals, you're constructing a tree. That is what this step says. Okay. Now let's move for this step C. What is this step C says? For I, j is equal to 1 to j to the power of m, compute gamma of jm. Okay, compute gamma of jm. So if you look at this algorithm, if you look at the algorithm, after constructing the tree, what you have done, you have taken the average of the leaves, right? You constructed the terminal regions. So you constructed the terminal regions, and then what you have done, you have taken the average of these values, right? Of different values ending up in the ending up in the same leaf. You're taking the average of them. So the steps is nothing but the mathematical proof of that. Okay, so that gamma of jm, which is the residual at that particular leaf node, is nothing but arg minimum of summation of gamma I mean the predicted value, comma f of m minus 1 of xi plus gamma. F of m minus 1 is nothing but the previous tree's predicted value, and gamma is the one which you want to find out, right? So now let's take an example of this particular node. Let's suppose in the previous tree, we came up with this one, right? The output for each leaf in is the value for the gamma that minimizes this summation. So this is the tree we got, and this gamma is nothing but the output value for each leaf is the value of gamma that minimizes the summation. So that we are trying to find out the gamma of jm. Gamma of jm is nothing but the residual at that particular leaf node. It's equal to arg minimum of gamma. We need to find out the minimum value of gamma, which we need to find out the gamma value, minimum gamma value that minimizes the summation. So if you look at the summation, this means j is equal to, since this is the second leaf and m is equal to 1, this is the first tree, we know that. This 2 indicates the leaf and this indicates the tree. Now, if you expand this summation, if you look at this, so these two samples are responsible or ending up in this particular residual. So since only two samples x1 and x2 go to this particular leaf, in this summation to calculate this gamma of jm, we only consider these two records. So xi belongs to ri comma j. Okay, so for this particular ri comma j, only these two records are responsible. So you only take those two records. Okay, so when you calculate the gamma of jm, you only take these two records because only these two records are ending up in this particular leaf. Okay, now then only x1 and x2 are used to calculate the output for R12. Okay, now going back here, now plug in the loss function. What is the loss function? We know off minus observed minus predicted whole square is the loss function. Now when you expand that, you will get this 1 by 2 into y1. Okay, so you have two records. This is y1 minus f of m minus 1 xi plus gamma plus 1 by 2 into y2. This is the y2 minus f of m minus 1 into x2 plus gamma whole square. Okay, so this is the expansion of this loss function. You're replacing observed with yi, predicted with f of m minus 1 into xi plus gamma whole square. So when you do that stuff and substitute the values, y1 is 88, y2 is 76. You are substituting these values now and plug in 73.3 for f of m minus 1 x into f of m minus 1 x2, because this is the initial leaf. So the predicted value, the previously predicted value for both the samples is the same 73.3. So I'm actually replacing both the values f of m minus 1 of xi, f of m minus 2. So for both these samples, the initial for not only these two samples, for any sample, the first predicted value is 73.3, which is the average of all the values. So for x1 and x2, the previous value is always the same 73.3. So I'm replacing that particular value here. Now I need to take the derivative of this, so that, and equating that to 0 will give you the minimum value for gamma. Now I take the derivative of this particular equation. So I'm just expanding the 88 minus 73.3 will give 14.7. 76 minus 73.3 will give an 2.7. Minus into plus will give minus gamma. So this equation turns down to this, and taking the derivative of this will give this. And now if you calculate the gamma, it is nothing but 14.7 plus 2.7 by 2. Okay, which is nothing but the average. We end up taking up the average. That is why I told you to take the average. The average is nothing but minimizing the calculating the minimum value of that residual, um, by applying the loss function. So when you calculate, the minimum value is coming down to be just the average of those two numbers. So this is how we ended up calculating the average of the values or the residuals for coming up in the same tree. That is what step 3 is. Now if you want to understand step 4, I mean in the part D in the step 2, it is nothing but f of m of x. Now the new tree is nothing but m is 1 now, is nothing but f of f dot of x plus b is, which is nothing but the learning rate, and this is the tree gamma of m. Okay, summation of all the trees. Okay, um, so the new prediction for the first sample is for 74.2, which is slightly less. If you calculate this weight for the sample, again we have done that 73.2 is the initial prediction 0.1, plus we came up with something called as residual, which is 8.7. Okay, this is a summation of the residuals, right? J is equal to 1 to j of m, gamma of j. um, So this indicates just the output of this particular tree. So which comes to 74.2. So we made a single step in the first sample. The new prediction for the first sample is 74.2, which is slightly closer to the observed value 88 than the first prediction 73.3. So this 74.2 is much closer to 88 than 73.3. That means we take a smaller step towards the right direction. And finally, if m is equal to 2, then f2 fx is the gradient boost algorithm. If you calculate the m is equal to 2 in the real world, for m is equal to 1 to m, we take m as 100, but if you restrict that to true here, this will be the final output. So that is the final step in the gradient boost algorithm. So this is how we made the final prediction, which is the continuous value. So given this sample, we add 73.3, and if you take this particular first tree, where it went, height is less than 1.55, which is true. So the residual will be 17 minus 17.3. So that becomes learning rate into the residual made by the first tree plus, and if you calculate the second tree again, height is less than 1.55. So in the second tree is giving minus 15.6. So 0.1 into minus 15.6. So the final value is 70. So we predict the height weight of this particular person as 70. This is how gradient boost algorithm works for regression, where we predict a continuous value. Okay. So this is just an algorithm, just a repetition of what the initial initial thought we have done. So what we just understood is why we have taken the average value for the residuals ending at the same leaf node, and also how we came up with the average value for predicting the initial leaf node. So that is just like taking the derivative and equating to 0 of the loss function. It will always gives you the average as the best value representation for those things, or the minimum value that gives you the minimum gamma value or the residual value. Okay, so that is what gradient boost for regression algorithm looks like. It's a three-step with the input. The first step, you make a initial prediction, which is f naught of x. In the second iteration, in the second step, you iterate for m is equal to 1 to m. Here, in every case, you calculate the residuals, and mm, and then what you do, you construct the regression trees, and then you find out the gamma value, which is a arg minimum gamma of summation of the loss functions. Um and finally, you update the tree with the initial predictions plus, which is the initial prediction plus the next tree's prediction summated with, you know, learning function. So it keeps on moving like this. So next step of f of m minus 1 would be this complete thing plus v into summation of I2. The new tree will get appended in every iteration. So that is how you keep on going, constructing multiple trees. So this is the first one, second one, third one, fourth one. You keep on doing that. And the final thing is output f of m of x. So this is the output. So whenever you fed some data to this, when you fed some x to this, the value will be calculated. So f of x is nothing but the function that calculates the predicted value. Okay. So yeah, that's how gradient boost for regression works, and that's how boosting technique is applied here. Is that clear? Hello.
Yeah.
Yeah. So that's all about gradient boost for uh, regression. Right now, you need to understand gradient boost for classification. So in classification, what you do, um, in classification, you predict yes or no's, right? Whether it's a dog or cat. It would be a categorical variable. So how does this gradient boost can be applied for classification is what we are going to see now. Okay, with that, we will be closing today's session. For understanding this algorithm, we won't go for algorithm for gradient boost for classification right now, because you need to understand what is log of odds, log of likelihood. You will be able to understand, I mean, those concepts will be covered with linear regression and logistic regression. So linear, logistic, and nonlinear regression. By now, you understood what a regression is. Regression is nothing but predicting a continuous value. Okay. Um, so that regression algorithms, linear regressions, nonlinear regressions, and logistic regression will be covered in the next week. So by then, you will get to know all the concepts that are required to understand XC boost, and there is another boosting technique which is called as XC boost. We will discuss all of that um, um, uh, after completing the linear regression and logistic regression. But for now, I'll just walk you through the gradient boost algorithm for classification, not the, I mean, the technique, or the technique, but not the algorithm where we have the mathematical representations. Okay. So gradient boost for classification, again, it looks almost similar to the regression case, because it is just the gradient boost. Why we call it as gradient is not, we are trying to calculate the arg minimum value. Arg minimum value is nothing but the gradient descent. So we are taking one step at a time. We are moving closer to the um, observed value, right? So that's why it is called as gradient. So gradient boost for classification. Okay, this algorithm will run in the similar lines of gradient boost for regression, but the mathematical calculations will slightly change. Okay, uh, right. So the first step again in the gradient boost for classification is predicting for the initial prediction for every sample. So there you have done the initial prediction for all the samples by taking the average of all the values, right? But here, how do you make the initial prediction for all the values for every individual? Here is by taking log of odds. Okay, I'll again walk you through the log of odds again when we encounter this log regression right now, but let's take that as just a single value, log of odds. Let's consider that as a value for now. Let's understand log of odds as a some value. Okay. Um, so It's a let's talk about that. Let's take that as an again average kind of stuff. So if you want to calculate the log of odds for this particular data set, how do you calculate the log of odds? Is nothing but log of the number of predictions. I mean the number of predictions which is made as S by the number of predictions which are made as no. That means so 4 likes this movie loves troll 2 by 2 didn't like. This is how you calculate the log of odds. Okay. So 4 people in the training data set loves troll 2 and 2 people in the training data set doesn't love troll 2. So if you want to calculate the log of odds for this, that will be nothing but log of 4 by 2. Why the log of odds is is calculated by what is this log of odds and why do we calculate this way? I mean, let's not bother about this at this point of time. I'll explain you when we come through the logistic regression again. But that is how you calculate the log of odd. So that value which is coming down as 0.7. Okay, log of odds is 0.7. uh, Now this log of odds has to be converted to probability. Okay, so how do you convert the log of odds to probability? Is nothing but this is the formula that you use to calculate convert the log of odds to probability. So this is the formula that you use to convert the log of odds to probability. So e to the power of log of odds by 1 plus e to the power of log of odds. Okay, so e to the power of 0.7 by 1 plus e to the power of 0.7. It comes down somewhere around close to 0.7. So now I set a threshold. If the probability is greater than 0.5, I will say that as, uh, you know, uh, loves movie troll 2. If probability is less than 0.5, I would mark that as doesn't love troll 2. Okay. Now I set this threshold. It is user defined and depends on the business use case. You can set that particular value. Since the probability of loving troll 2 is greater than 0.5, we can classify everyone in the training data set as someone who loves troll 2. As 0.7 is greater than 0.5, and the probability that we have calculated by using log of odds is greater than 0.5. So we considered every person loves movie troll 2. So the initial prediction, that would be the initial prediction. Okay. Initial probability that we have calculated is 0.7, and that says every person loves troll 2. Yes, 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 yes. Everyone loves troll 2. So while 0.75 is very common for making classifications, we could have just done easily used a different value. It depends on the business case. Okay. You can set any threshold. You can set if the probability is greater than 0.6, then you consider that as true or the one case. So if probability is greater than 0.6, then you can say that person loves troll 2. If it is less than 0.6, you say the person doesn't love troll 2. Based on this value, your prediction will be dependent. Your prediction depends. But for now, as I set threshold to 0.5, and the probability that we have calculated using the log of odds is greater than 0.5. So I'm predicting I'm predicting every person loves troll 2. That is the initial prediction that I'm making. So the initial probability is 0.7. So this is the initial prediction that I have made. And I am predicting every person loves troll 2 movie. Okay. And now the second step is what we have done there. We have calculated the residuals. So there, how we have calculated the residuals is nothing but the observed minus predicted, right? Okay. So we have taken just the difference between the observed and the predicted. So these are categorical variables. Now we need to move them as um, um, some probabilities. Okay, if you take this particular diagram, so one, if the person likes movie troll 2, we are saying the probability of that case is 1. If the person doesn't loves troll 2 movie, we say the probability of that person is 0. Okay, probability of loving troll 2 of a person who doesn't love troll 2 is 0. Probability of a person loves troll 2 movie would be 1 if he loves probability of movie. That is obvious, right? So the actual probabilities is this 1. For S it is 1, for no it is zeros. Okay, that is what it actually means. Now what we have predicted, for what is the probability that we have predicted in the first step, it is 0.7 is the predicted probability. Now taking the residual is nothing but observed minus predicted. So 1 minus 0.7 will become 0.3. So now this is the predicted value for predicted probability 0.7 for every sample. So now we take the difference between these two, observed minus predicted. So 1 minus 0.7 will become 0.3. Similarly, you calculate the probabilities or residuals for every sample. So if it is no, it is 0. 0 minus 0.7 will become minus 0.7. Okay, so this is how you calculate the residuals. Now, again, like regression, you use these variables to predict these residuals. Okay, now you will build a tree using like popcorn, age, and favorite color to predict the residuals. So you will construct a tree to predict the residuals. Now, this is how the tree looks like. Okay, just like when we used gradient boost for regression, we are limiting the number of leaves that we will allow in the tree. So we are limiting the number of leaves to be 3 here. Okay, again, in general, the number of leaves will goes to 8 to 32 for the classification as well. And now we got the tree. And what we have done in the regression case, initial prediction plus learning rate into this tree, right? And we use that value for the calculation. But as these are probabilities, as these are probabilities, you cannot directly use them. Okay, so calculating the output values, so these two leaves goes here in that particular tree, these two leaves goes here, these two leaves goes here. So and the next step we have done is you have taken the average values there, right? You have taken average values for these the residuals falling in the same tree in the regression case. But as these are probabilities, you cannot just take the average of them. Okay, there is a different way of calculating those values. Instead of average, you will do something else here. Okay, that's the only difference between those two things. Um, when we use gradient boost for regression, a leaf with a single residual has an output value equal to the residual. Okay, when you have a leaf with single value, that would be the same value, right? You're not taking a average or something. When you have a single value, that would be the same value here. This is because the prediction. So these leaves are derived from the probabilities, right? So as I told you, you cannot directly just add log of odds prediction without some sort of transformation. You need to transform all these values. Okay, as these are probabilities, as these are calculated from the probabilities, you need to do some sort of transformation. Uh, because every transformation is in the form of every predictions are in terms of um, log of odds, right? So these leaves are derived from the probability, so you cannot directly you need to do a transformation on them. You need to transform the probabilities. uh, so the transformation is done by, you cannot directly use them in regression. You would have directly used the residuals there because those are actual values, these are probabilities. So you need to transform the probabilities back again. Okay, so to transform the probabilities back again to back again using this formula, which is sum of residuals by summation of previous probability into 1 minus previous probability. So the numerator is nothing but the summation of the residuals. So for just for giving an example for you, so if you want to convert this particular leaf node, which is minus 0.7, this is the tree that you have constructed, and this is this tree that you have constructed, and this is a leaf node. Now we are trying to transform this leaf node. You need to do a transformation because you cannot deal with the probabilities when you're converting the values, or when you're using these values. You cannot directly summate these values with the initial predictions. You need to transform them. You need to transform these probabilities. Now, if you look at this, 0.7 minus 0.7 is transformed as minus 3.3. How does this transformation happen is that this is how it happened. So this minus 0.7 is the residual. Okay, residuals are nothing but the probabilities that, I mean, we predicted the residuals, right? So the residuals are nothing but minus 0.7. So as we have only one residual, there won't be any summation. And also there won't be any summation as we have only one single sample. So for this sample, the previous probability, what is the previous probability of this? The previous probability is 0.7, whereas For every sample in the first iteration would be having the same probability. That is what we have done in the first step, right? In the first step, what we have done, we predicted the probability of all the samples to be 0.7. Okay, so that is the initial previous probability. As we move on to the next steps, that probability will keep on changing, but for the first step, it would be 0.7 only. Okay, so the previous probability is 0.7 for this. So we applied the math in the numerator, which is minus 0.7. In the numerator, the previous probability is 0.7 and 1 minus previous probability, which is 1 minus 0.7. We are just using this formula and we calculated the value. So minus 0.7 transformed value is minus 3.3. Okay. Similarly, for this node, we are calculating the transformed value, which is summation of residuals. There are two residuals here, 0.3 and minus 0.7. We summate both of them in the numerator. And what is the previous probability for 0.3? It is 0.7 into 1 minus 0.7. What is the previous probability for this residual? It is 0.7 into 1 minus 0.7. Okay, we calculated the residuals, right? So these are the residuals and these are the previous probabilities of all of this is 0.7. Okay, so we calculated that value and we are getting a single value for this. And now to calculate the value for this, you again apply the same formula. Sum of residuals by previous probability of the residual is 0.7. This 0.7, 0.7. 1 minus 0.7. You solve this equation, you get this one. So the new tree will look something like this. So log of odds, which is 0.7 plus so this is log of odds. This is the probability. So you need to convert back the probabilities to log of odds. So that's why you are not, these are probabilities, right? These are probabilities. You need to convert them to log of odds. So everything has to be in the same scale. Now we are ready to update our predictions by combining the initial leaf with the new leaf. Okay. So just like before, we have taken the learning rate, which is 0.8. Now you got a complete tree with the transformed values. So now you again do the log of odds prediction. For this particular sample, what is the log of odds prediction? Initially, it is 0.7 and it falls here. Color is equal to red, which is false. So it goes here. Here it is blue, right? It is not equal to red. So it comes here. A is greater than 37. A is 12. So it is false. So it comes here. So it falls here. So the value of this is 1.4. So 0.8 is the learning rate, 1.4. So we got the log of odds as 1.8. Again, we calculate the probability, which is 0.9. Probability is calculated by e to the power of log of odds by 1 plus e to the power of log of odds. So I'll show you how this transform, why we are applying this transformation and why we are doing it. It is just converting the probabilities to log of odds again. Okay, that derivation I'll show you when I explain you the algorithm stuff. Okay, but for now it is 1.4, right? Now the new logarithm, new log of odds calculated for this particular record is 1.8. If you calculate the probability, it is 0.9. So initial prediction that we made is 0.7. Now the new prediction after the first t is done as 0.9. It is coming close to 1, right? The actual prediction of this is 1. So with one step, we are moving, we are making a step in the right direction by just making one step. It reduced from 0.7 to 0.9 and it came close to 1. Okay. So we are taking a small step in the right direction since this person loves troll too. And if you see the other case, now I have calculated the similar way. In the similar way, I have calculated the predicted probabilities for all the samples. The same way. For the second sample, 0.7 plus 0.8 into, you can just, I'll explain you the same one, 0.6 into 0.7 into 0.8 plus, color is equal to red, false. This comes here. A is greater than 37. So it is true. 0.3, it comes here. So it is minus 1. So 0.7 minus 0.8, which is minus 0.1. So this is the log of odds. Now you have to apply e to the power of minus 0.1 by 1 plus e to the power of minus 0.1. So that gives you this 0.5 value. Okay. E to the power of 0.1 by 1 plus e to the power of 0.5 gives 0.5. So if you look at this value, this new predicted probability is worse than before. Initially, we made a prediction of 0.7, but now we predicted that as 0.5. The actual prediction is 1. The observed predicted probability for that particular sample is 1. Initially, we predicted that as 0.5, and now we are predicting it as 0.5. That means you are going far from the actual prediction. So this is worse than before. And this is one of the reason why we build a lot of trees and not just one. So when we keep on building multiple trees, which are wrongly classified, will be corrected in the, will be emphasized more when we construct the next tree. That is what boosting algorithm is. Now we calculated all the predicted probabilities, and now it is easy to calculate the residuals. How do we calculate the residuals? Again, observed minus predicted. What is observed? 1 1 0 0 1 1. So you do the same. 1 minus 0.9 will come 0.1, 0.5 minus 0.5, because it is a 0. 0 minus 0.5 will become minus 0.5. So here 0 minus 0.1 will become minus 0.1. So this became closer, right? Like 1 minus 0.1 will become 0.1. 1 minus 0.1 will become 0.1. Again, this is the second step, right? uh, so this is the second step. Again, all the probabilities we know, the for the right, for the person who loves probable, loves movie troll 2, the probability is 1. Who doesn't love troll 2, the probability will be 0. Now we again calculated the residuals. We can construct the tree to we can construct the tree to predict these residuals by using these variables, and now again recalculate the residuals. I mean, these probabilities are converted back to, or scaled transformed by using the formula, which is summation of the residuals. What is the summation of the residuals? These are the summation of the residuals. Now, for this particular sample, what is the previous probability is what we have to understand. Okay, if you look at this, these four samples fall at this particular leaf. Okay, for this 0.1 residual, the previous probability is 0.9. So previous probability into 1 minus previous probability. For minus 0.1, the previous probability is 0.1. So probability into 1 minus 0, 1 minus previous probability. For the next sample, which is 0.1, summation of the residuals by summation of the probability into 1 minus probability rate. So for 0.9, the probability is 0.9. 0.1, the probability 0.9. Probability into 1 minus previous probability. And for this record, 0.1 and the previous probability is 0.9. So this is how you transform the values. So that this, after solving this equation, we get 0.6 for this. Okay. Similarly, you calculate the transformed values for all the nodes of this particular tree, and then you come up with something like this. So this is the initial prediction made, log of odds calculated, then this is a new tree constructed, and these are the residuals, and these are the transformed values. These are the residuals, these are the transformed values. How do we transform the residuals to how do we calculate the transformed values from the residuals, which are the probabilities? It is nothing but the summation of residuals by summation of probability into 1 minus probability. These are previous probabilities. That is how you calculate the, what do you say, log of odds. Okay, now if you want to make a prediction, once you constructed the, now in our example we just stopped after constructing two trees. In the real world we go up to 100 trees. Now how do we make the prediction when we get a new sample, right, using these samples? Now we got this particular record. Okay, now let's calculate the log of odds for this. 0.7 is the log of odds plus the learning rate is 0.8 into passing through this particular tree. Color is equal to red, which is false. Here it is green, right? So here color is equal to red is false, so it comes here. A is 37. Okay, A is 25. This is also false, it falls here. Okay, when this record is passed to this particular tree, it falls here. So log of odds comes down to 1.4. So 0.8 into 1.4 plus the learning rate of the second tree, which is 0.8 into what is the log of odds, the transformed value. So A is less than 66, A is 25, true, so it comes here. As this is true, it comes on to the left side. A is greater than 37, it is false. 25 is greater than 37 is false, so it falls here. So here the log of odds is 0.6. So that is how you calculate the log of odds, and the log of odds value is 2.3. And if you want to calculate the probability of this, again use the formula of, how do we calculate the probability from log of odds? E to the power of log of odds, by 1 plus e to the power of log of odds, right? Log of odds. This is how we calculate the probability. So after applying the log of odds, from the log of odds, you are calculating the probability 0.9. So the probability for this record is 0.9, and we have this threshold set to 0.5. As 0.9 is greater than 0.5, we are predicting that this person loves troll 2. Okay, so that is how you do the classification using gradient boost. So the only tricky part is you're switching between probabilities and log of odds. That is the only thing. So when you are the residuals here are nothing but the probabilities. So when you construct the trees using those residuals, the leaf nodes will have the probabilities. So you need to transform the probabilities back to log of odds. Okay, so that transformation is the only tricky part. Whereas in the log gradient boost for regression, you don't need to do any transformation. Residuals are all the continuous values. The actual there is no transformation between probabilities and log of odds in the regression. It is all the same scale values, the weights in every case. So you are taking the direct values. When multiple nodes are falling at the same place, you are just taking the average, because the average is the value that gives the minimum value, right? Minimum value of the predicted value in the loss function. So you take the average. Here you do that transformation, which is sum of residuals by summation of probabilities into 1 minus probability. So once you calculate the log of odds, again convert that to probability, and once based on the probability and the threshold that is set for your logarithm, you predict whether that person loves troll 2 or not troll 2, whether it can be any case. That is how you do the um, you apply the gradient boost for classification. So after this session, you are left with the algorithm explanation for gradient boost for regression, and how the transformation from probabilities to log of odds, log of odds back to probabilities, how the probability is calculated by using log of odds, how do we derive that formula of e to the power of log of odds by 1 plus e to the power of log of odds. All that will be covered under algorithm explanation of this particular gradient boost. And there is only one other algorithm which is left, which is xg boost. Those two will be covered in one of the sessions after completing linear regression and logistic regression and nonlinear regression. When we study about logistic regression, we will study about this log of odds and log of likelihoods. And once you get that clarity, you will understand the things that we want to understand today, the transformation and all that stuff. So by end of today, we are left with few more concepts. One is linear regression is something that you have to understand. Yeah, so to just give you an outline of what we are left still means. So this is how this is what we are. I know we are lagging behind lot of time, around a month, but I have prepared the Python notes. So that is what I plan to cover in December. So you have the notes with you. It's on you to cover that. So this is what we are left with. So linear regression is pending, that we need to study, and non-linear regression. So linear regression is one thing, non-linear regression is one thing that we need to study, and logistic regression. These three fall under one category, logistic regression. Okay, once this is done, we have in clustering we have few things to cover. One is kernel based clustering, sorry, kernel density functions, kernel density function. And then we have Denclu algorithm, which which is from which is based on kernel densities. And we have subspace clustering, uh, and then we have something called as gradient boost for regression algorithm. Gradient boost for regression algorithm is pending, and then XG boost is pending. XG Boost is pending. So these two falls under boost algorithm. I mean boosting technique, which is ensemble learning. Boosting, these two falls under boosting. We covered most of the boosting, but these two are pending. So to the entire machine learning is left with only 3 sessions. So this will be in one session. This will be in one session. I think this will be in 2 sessions. So 3 sessions, I mean 3 classes, and this will be in one session. 4 sessions are pending. So I think 2 weeks. So if we take 2 sessions in one week, so it will be covered in 2 weeks. So that with that we will be done with all the theory sessions, and I will also share you. I mean Python is shared, and now I will create a notebook for uh, NumPy, and I'm in the process of doing that. But I'll be done by once we complete all these theoretical sessions. I'll also be done with that. But I'll walk you. I'll I'll provide explanation for the both the libraries because they are hard for the machine learning. Even for anything, they are hard. So we move by going to by learning that two libraries, pandas and numpy, and we start implementing all these algorithms in Python. So once that coding is done, coding I don't think it will take long time. So it will be most probably just we can complete in 3 sessions. The whole coding for all what we have learned so far in machine learning can be covered in 3 sessions, 3 to 4 sessions most probably. So with that we will be done. So that's the plan going forward for machine learning. So I need to complete the theory of all of this, and I have shared you one link, right? Let me stop recording.